Sure. So I'm going to talk to you about some work that is ongoing. It's in revision right now. Hopefully will appear online soon. We've been doing work on secular change through Earth history, focused particularly on the compositional change of rocks, the oceanic crust, the continental crust through time. And the continents, in fact, tell quite an interesting story for one of the problems that we see in the geological record, in that we don't have orogenic or any other types of UHP eclogites past a certain point in time. So this kind of field photo on the front page will become apparent quite soon. But to start off, and this is a question that's already been raised a few times, when did plate tectonics start on Earth? I would say that despite previous comments made in the first talk, there's certainly no consensus that plate tectonics initiated at a global scale in the Proterozoic. In fact, if you tabulate and look in detail at most of the evidence, isotopic, tectonic, geochemical, modeling evidence, a lot of convergence seems to come to this 2.9 or 3 GA period of time, which is during the late Archean. One good example of this is the oldest supercontinent, which is Kennerland, 2.7. It's going to be hard to envisage accumulating crust in one place to form a supercontinent without a global network of subduction zones. So this figure here is presenting an overview with a bit of argument for why you might say plate tectonics was operating at a certain time. And with plate tectonics comes subduction. So if we take the view that subduction has been operating since at least 3 GA, and just a quick segue here, if you want to read about the arguments for that, I'll just put a quick link to this recent review paper that we have online. So if we assume a 3 GA point in time, well, why do we not see eclogites in the geological record from at least that point in time? Another question you might say is, why is constraining the age of plate tectonics a problem? And it's because a lot of the indicators we will use have different weights of reliability. Focusing on the petrological arguments, things like blue schists and eclogites, a lot of them are extremely young. The oldest blue schists are Neoproterozoic, 0.9 GA. The oldest eclogite itself is the oldest subduction-related eclogite is around 2.1 GA. But that's not a UHP example, that's actually just a HP example. And for those who maybe aren't familiar with the difference, the HP-UHP transition is the quartz-calcite transition, which occurs at about 2.5 gigapascals, so about 100 kilometers depth within the Earth. So I previously discussed secular change in oceanic crust composition, the cooling of the mantle over time, the decrease in mantle potential temperature since the Meso-Archean has reduced the maficity of oceanic crust over time. The primitive oceanic crust in the Archean was much more mafic than modern-day morbus. And this is purely a function of the cooling of the Earth. Now, this has implications for the phase petrology and the physical properties of rocks that are subducted down the channel into the mantle. And we've already kind of dealt with this for oceanic crust. There's a paper in 2016 where we talk about the blue schist problem. But what about the continents? So the whole impetus for this talk, this bit of research, is what if the continental crust changed in composition as well as the oceanic crust? And there's a lot of geochemical evidence or studies out there that suggest that it has changed in composition through time. In particular, using these proxy analyses, trace element ratios and glacial diamectites and other types of analyses, a lot of studies are coming around to the idea that the Archean crust was much more mafic than the modern day crust. As we know, the continents today are roughly andesitic in composition, so they were plotted on a task diagram either within the andesite or the dacite field. But I've labeled here some data presented by Chen et al. 2020 in GCA, and they're not the only study to propose this. This is just the most recent set of data that I've incorporated into this work. They're suggesting that the bulk composition of these mafic continents were actually closer to basalts or basaltic andesites. And this is highly significant for how the Archean continents would behave if they were to be buried or subducted. So Archean continents were not as felsic as modern day crust. One problem with this argument is these geochemical proxies are sampling the upper continental crust, the UCC, as opposed to the entire continental crust. And there's arguments and there's discussion to be had there about whether the UCC is a good proxy for the entire continental crust or not. But the purposes of this, we'll assume that it does represent the entire crust, which in the early Earth might not have been as well differentiated as we have today. So if we look at Phanerozoic UHP eclogites, such as in the Himalaya, we have Somawari and Kagan. We have examples of mafic dikes that have been intruded into continental foreland prior to subduction. Then the entire terrain is taken down the channel, the entire terrain is metamorphosed, and it's exhumed again. And it's exhumed because the felsic crust is more buoyant than the surrounding mantle. So can you have this same exhumation if you had a changing composition of continental crust and if the Archean was much more mafic than the Phanerozoic continents? That's the question to be answered. So what we did is we used Chen's data actually. So this figure was from our paper, but the numbers at the top have come directly from Chen et al. 2020. And the schematic sections that I've drawn up here, the Archean is one to focus on, of course. You'll recognize the Phanerozoic one from the Hawksworth 2006 paper. It's one of these sections that's reproduced in lots of papers. It's nice to show the thickness and petrological variation. So going backwards in time, data from Chen and other studies, and in one part of the Roberto Glidner group coming out of California, would suggest that you have a higher proportion of greenstones and komatiites in this older continental crust, which gives it a more mafic bulk composition. So lithologically, it still contains plenty of TTGs, has greenstones, has komatiites, but its bulk composition is lower on the silica dioxide axis. So on a test diagram, it ends up plotting further towards the mafic side. It was thinner and less differentiated, more undifferentiated. And this to me is one of the arguments that we're using in the study to say that the UCC is actually probably quite representative of the crust as a whole. This young continent has not had a chance to differentiate in the same way that modern day continents will. Now there's caveats to this kind of modeling. On the left is a really nice summary diagram from Claire Warren, who was doing a News and Views article on a Nature Geoscience paper by Owen Weller, talking about the trans-Hudson eclogites, which feature on one of these diagrams on the right-hand side. But just to focus on this left-hand side diagram first, this work is focusing on orogenic eclogites. So these are eclogites, Himalayan type eclogites, where you have intrusions of mafic rock into continental crust. And then these terranes are subducted at convergent margins. So it's not focusing on wholesale subduction of oceanic lithosphere. And we do have slices of exhumed oceanic lithospheres that have reached eclogite facies. But discussion of the compositional change over time of oceanic lithosphere is being done, and it's not to be focused on in this particular piece of work. So the continental margin approaches the subduction zone is thinned, telescoped, and dragged down because it's still attached to the descending root. It's then metamorphosed, and it comes back up the same way, we think, in most cases, to be exposed again at the surface. So here's the distribution of metamorphic rock types through time. This bottom one is the point here. We have eclogites way back to about 1.82 GPa. If we look at the composition, there's previously defined compositions by Chen et al., how the mineralogies and the densities of the rocks behave through time, we see something really interesting. So looking at upper continental crust, UCC, at these three different points in time, 0.3 for Phanerozoic, 2.4 for Proterozoic, and 3, GA, as an example of the Archean mafic crust. The intermediate and the felsic versions, the post 2.5 GA crusts, never achieve a buoyancy that will, they never become more dense than the surrounding mantle, of course, because they're too felsic. Silica-rich rocks will never do that. So they always have the potential to be exhumed back to the surface. But for the case of the Archean basalts and the Archean mafic crust, it crosses the transition between the density of pyrolite at about 2.2 GA, which is actually before you've reached the HP-UHP transition, which is a greater depth than the Earth. So you might infer from this that eclogites are being made, UHP eclogites could be made by the subduction of mafic Archean crust, but they can never be exhumed against the surface because they're so buoyant. So as soon as they transform into coesite-bearing UHP metamorphic works, they can't come back to the surface. It's unlike the modern day examples where we have this buoyant felsic crust that is acting as this mechanism to return them. There's fine detail here. There's hydrous versus nominally anhydrous examples. This is stuff that can be looked at in detail. One of the preprints is online for this, so you can read about that in more detail. The result stays the same for each. Because the arguments about the composition and the petrology of the Archean crust are quite vigorous, we did do some sensitivity testing of this result. So we checked how variation of the Mafic Archean crust affects these density transitions. And it turns out there's some box and whisker plots here showing how many of those Monte Carlo results actually do have this similar transition point before HP UHP transition is reached. And in around 75 to 89% of cases, these subducted or buried, equally valid for buried Archean continents that are more mafic in composition, will become less buoyant. They will not be able to return to the surface because they're denser than the surrounding mantle. So conscious of time, so I'm going to skip to some more conclusions. There's some interesting implications of the Archean continents being more mafic. One of them is that they will have a different lithostatic strength envelope or crystal strength envelope to modern day continents, which are more felsic in composition. So the long and short of this, there's too much here to really summarize in detail. But the Archean continental crust, if it is entirely mafic in composition, would have a contiguous strength envelope, something called a creme brulee type strength envelope. Whereas Phanerozoic continental crust, which is more felsic in composition, would have a weak lower portion. This is called a jelly sandwich model, where you have strong, weak, and strong in the lithosphere itself. And it turns out that these Archean mafic continents would therefore behave and look like oceanic crust as opposed to continental crust, basically because they're mafic in composition. This has implications for geodynamic models, which we see a lot of, trying to look at how Archean continents may have evolved. There's two main end members for the vertical transport of crustal materials into the mantle. We have long wavelength delaminations and short wavelength drips. And it turns out, yeah, thanks, Owen. It turns out that you need a kind of weak middle layer in your crust, in your lithosphere, to allow these long wavelength delaminations to go down. So one of the discussion points we have in this study that is hopefully soon to come online is that delaminations actually aren't very likely because you have this stronger Archean crust than you were expecting. So the conclusion slide, I went out a little bit over time. If we take the standpoint, the Archean upper continental crust was more mafic than today, then that actually would have prohibited UHP eclogites from being exhumed. If we look at orogenic eclogites themselves, Himalayan type eclogites, it did not stop them from forming. So this harks back to a comment that was made earlier about preservation biases. These rocks were still formed, but you could not have seen them return to the surface because they didn't have the buoyancy to be returned. I've kind of covered the stuff about the LSA, but there's one more thing that's interesting about the Archean continents being mafic, in that mafic, they're thinner and they're denser, so they would have sat lower down. And if we do a calculation for the volume of the oceans back in time, we see that a lot of the Archean continental crust would have been submerged, basically because of its higher density, its more mafic composition. So this is backed up by isotopic evidence. There's a recent study by Ben Johnson and Boswell Wing, who say that continental emergence had not happened in the Archean. It happened towards the Archean Proterozoic boundary. And this kind of petrological hypothesis, this petrological study supports that. It has implications for life that rely on subaerial land, these warm little pond models. So there's implications there. I'll stop it there. Thank you.
Thanks, Richard. You stopped it pretty much at the 15-minute mark. I can't see any questions, so I guess I'll just ask a quick question of lots of present-day Archean crust, is broadly tonalitic, trondhjemmitic in composition, and that obviously would go against sort of or that would remain buoyant. So I guess that really relies on that komatitic crust in the Archean, like how, in your sensitivity testing, I guess, was that across lots of different compositions?
Yeah, so the sensitivity testing did test this, and as we responded to one of these comments that came up in review, saying the exact same thing to you, I don't know if it was you, Alan. these TTGs are exposing the middle crust. And of course, we're focusing on the upper continental crust as well, which will be much more mafic. That's why the basalt's being erupted. So the pressures that you calculate for the emplacement of these TTGs tell you that they're not at the surface. So there's an exposure level difference here. But you make a very good point.
Great. Okay, thanks.
These proxies should match up with natural observations too.
Sure. Okay, thank you, Richard.